Hi, good morning, everyone. I hope you're doing well out there. We're moving into our 14th week of class, and we're getting ready to have our third exam. So that's going to be this Friday. I'm not going to assign any new homework this week except for to study for the exam. Well, I take that back. I will assign a reading assignment later on this week. So there will be a reading assignment for next Monday. I'll probably assign that on Thursday or Friday. So please keep an eye out for that. But other than that upcoming reading assignment, please just take your time to study for exam 3. That will be on chapters 7 through 9. There's already a study guide up on Canvas. The format will be pretty much just like the previous exams, nearly identical to the last one. And it will be available Friday at 2 p.m. and I will have it open for you to take until 11:59 p.m. Sunday. Now, keep in mind, again, it will be a timed exam, so once you open that up, you'll only have an hour to complete it. Yeah, and I will be posting a review lecture like I did last time. So Wednesday's lecture will be a review of those 3 chapters. I don't think I have anything else to say on that. So let's go ahead and get started with today's content. We're going to be wrapping up chapter 10, talking about global warming. So let's look at that. Here's a diagram of global warming. And basically, well, this isn't a diagram of global warming. This is a diagram of the average global temperature for the last century or so. You can see here from 1880 out to their data stops at 2014. So it's a little out of date, but nonetheless, you can see what's going on here. So the idea is that the Earth is warming, and this is data showing that. It's warming what we think is basically through a greenhouse effect, as that we get more CO2. As we increase the atmospheric CO2, the greenhouse effect strengthens and it warms the planet. So we can see here that there's a fairly steady increase from about the early 1900s all the way up to the present day. Now it looks like it's cooler in this region back here, but realize that this is an average over the entire 20th century. So if it's been warming over that period, newer times will appear warmer and older times will appear a little bit cooler. So, but we still see a steady increase. And right about here was the start of the Industrial Revolution. Now, to be completely fair, our reliable data only goes back about 50 years. So back until about the 1960s, 1970s, that's the only real reliable data that we have. Looking at weather stations around the planet, looking at seawater temperature from ocean liners and seagoing vessels taking water in, things like that. Before this time, we weren't really taking data, and so we've had to get those things in this information a variety of other ways. So we do see an increase in average global temperatures, and we talked just a minute ago how this is related to CO2 increase. So here's a couple of graphs here on the left where we have the temperature change in this top graph and CO2 parts per million in the atmosphere in this graph. And what you should be able to see here is that whenever there's an increase in temperature, there's a spike in CO2. And whenever we have a decrease in temperature, we have a, whoops, my line's off a little bit there. We have a decrease in CO2. And so these two things track very well together. we could say that the CO2 and average temps are very well correlated. That is, when one goes up, the other one goes down. And one thing I'll point out here is that these graphs are on a very different time scale than the ones we just looked at on the previous slide. Those ones, that graph only went back about 100 years. This one goes back hundreds of thousands of years. So these are long time scale natural variations. Remember, we talked about the Milankovitch cycles and whatnot. So that's primarily what we're seeing here. Also, variations in solar cycles. The sun gets more active and less active, and that can affect the climate here on Earth as well. If we look at the very end of this graph, right here in the 1750s, 1800s, this is again the Industrial Revolution in the 1800s. And there's a huge spike there. Notice it's well above the natural variations. And if we zoom in on that part, that's what this graph is a zoom in on the last 100 years or so, you can see these CO2 levels really spiking up. And so this is a human-caused increase. Okay. And you may be wondering about these little oscillations here. These are summer-winter variations. Because of the increased plant respiration, or photosynthesis, maybe I should say, during the summertime, plants get green, they have a lot more leaves, there's a lot more photosynthesis going on, and so we have small oscillations just on a yearly cycle there. Now, I just said that this is human-caused. There are people out there that claim that this increase in carbon dioxide and global temperatures are part of natural cycles. And I'm going to argue that because of the scale, not just the fact that they are rapidly increasing compared to the increases we saw in the past, but there are other reasons that these is a human-caused increase. So my question for you is that what is the evidence that this is human activity and not natural factors? So please take a moment and read these on your own and push pause. All right, it turns out that the correct answer here is all of the above. That this is all evidence that the increase in carbon dioxide is human-caused. So a couple things I'll point out here is that the atmospheric concentrations track almost perfectly with the amount of carbon dioxide released by industry. So as factories have ramped up, as we have more global shipping, we see increases in atmospheric carbon dioxide. So they track almost perfectly together. Scientists have looked at natural sources. We have good estimates for volcanoes and oceans and things like that, and they can account for no more than 1% of the rise. So this is taken into the models. There's a graph of this in your textbook if you'd like to look at it, what the models look like with just the natural causes and what they look like with human causes as well. Last thing I'll point out is the ratio of carbon isotopes is consistent with the burning of fossil fuels. So we've talked a lot about isotopic ratios in here, back when we talked about the moon, different things like that. So we have different isotopic carbon ratios in the past. Things as it gets turned into fossil fuels, that changes the ratio there. And so we can tell by studying this, to be honest, I don't know exactly all of the details, but by studying the ratios of, say, carbon-12 to carbon-14 to other carbon isotopes in the atmosphere, we can see where the source of this carbon is from. And you get different sources if it's plant-based versus geologic. I believe it depends on how the plants prefer one type over the other as they take that material up into their cell structures. All right. So I have a writing prompt for you here. So besides global warming, what are the consequences of climate change? And by global warming, we're thinking that the models predict a 2 to 5 degrees Celsius increase in global average temps by the end of the 21st century. So by the year 2100, these global temps should increase by 2 to 5 degrees C, which could be catastrophic. Now, I want you to think for a moment, what are some of the other consequences of climate change? Take a minute or two to write these down, and when you're finished, go ahead and push play again. All right, so a couple that your book talks about, which I'll point out first, are the melting polar ice caps and sea level rise. So there may be a 0.5 meter rise by 2100. That would be pretty catastrophic. That would cover pretty much the entire state of Florida and other low-lying places. So this would be especially catastrophic for low-lying areas. Another thing that would contribute to this sea level rise is not just the melting ice, but water gets bigger as it gets warmer. Everything does. This is called thermal expansion, and just by raising the sea level, the sea water temperature by a few degrees would make it expand enough to have a noticeable effect on sea level rise. So I'll write that it's not just melting ice, but it's plus thermal expansion. Okay. Another one is increased evaporation. Increased evaporation. We talked about this with the runaway greenhouse effect, that as it gets hotter, and we talked about it with the climate cycle, as it gets hotter, you get more evaporation. But that's going to cause more extreme weather. Would be a consequence of this. Now, we have to be careful when we talk about weather versus climate. Weather is a short time scale thing. Weather is on the order of days to weeks, at the most months, and climate is months to years to decades. So talking about very different things here. And with this more extreme weather, we could see things like more extreme droughts, hurricanes, stronger and more often, and even more extreme winters. By increasing the amount of water in the air, by increasing the temperature of the seas, we can change how the Earth circulates, both in the oceans and in the air, and that can really screw with weather patterns. And so we can actually get much more extreme winters in certain parts of the world. Yeah, so a couple things I'll add to this on my own, and this one is related to the extreme weather, is that we may get big changes in ocean currents. Some you might be familiar with are like the Gulf Stream, the Pacific Current, and locally off the coast here, we have the Humboldt Current. Now, these are vital for the fisheries industries and also have a big impact on weather. So, changes in ocean currents could come from the increase in water temperature. It can actually also come from the lack of sea ice at the poles. Sea ice causes cold water to sink down. If there's no sea ice, you don't have that sinking cold water, you can get really big disruptions in these currents. Last one I want to add here is ocean acidification. And this can cause problems with sea life. But what happens here is CO2 dissolves in the oceans. We've talked about that. But when it does, it forms carbonic acid. And this can wreak havoc on sea life with shells. Bad for shells, things like oysters, mussels, even corals, anything that uses calcium carbonate as their structure, that calcium carbonate can get destroyed by this ocean acidification. And so this might have big problems, at least in the short term, for how our planet sequesters carbon. Remember, it's the carbon shells of little tiny animals that then sink to the ocean floor and get built into limestone. So if those little animals are having problems building their shells, that may cause problems in sequestration. It also can disrupt the food chain. So these are the big two here. But these others are important as well. So that's about all I have today. Just a short lecture. But I want to encourage you to study for the exam. Now keep in mind, this last chapter we just wrapped up here, chapter 10, will not be on the exam. I don't have time to have you do a homework on it, and plus then I can make the final on chapters 10 and 11. I think we should have no problem getting through chapter 11 in the next week or so. So, yeah, if you have any questions, please feel free to email me. Study hard, take care, and be safe out there.